All right, we are about to begin this new subunit for the rotational chapter, which would be SHM, simple harmonic motion. Simple harmonic motion is generally defined as any system that has internal forces, which we'll talk about in a moment, that bring it back to its original position after it might be moved from some natural position away from some natural position. And once released, the internal forces would pull it back to its original position. A common example is the mass spring system, and another common example is the pendulum. Both of those are the two most common examples in introductory physics relating to this topic of simple harmonic motion. So this does involve Hooke's law, for sure, because it involves springs. And recall that Hooke's law suggests that the amount of restoring force that a spring provides as you stretch it out, amount of internal restoring force. And when we say restoring force, it just means that in this case, I'm applying a downward force to stretch the spring. Newton's third law says that the spring will therefore pull upwards on me, and essentially upwards on itself. It's an action-reaction pair. I pull down on spring pulls upward on block, if I'm holding on to the block. And that idea, again, is it's referred to as restoring force because after I release it, that upward spring force, which is pointing up right now, we're not referencing the downward force that I'm applying. We're going to be talking about the force generated in the spring. That's an upward force. So when I release it, it would restore itself back to its what we call relaxed length. Doesn't mean that it would stop there. So we'll notice that, for example, if I were to hit play on, oh, that's a little too much. Let's increase the spring constant. So if I were to pull this down, from its relaxed position, which is here, that would be, it's actually not its relaxed position, so that's worth pointing out. The relaxed position is actually the length it has when it's literally not under any strain. No forces are being applied to it, which you can see in the image above. On the other hand, when we do apply a force to it, like hanging it from a ceiling, putting a mass on it, this is actually referred to as the equilibrium position, the equilibrium length. So I shouldn't really call it its relaxed length. It's really its equilibrium length. And we call it the equilibrium length or equilibrium position because the system is in equilibrium in this position. That is to say, since it's not moving, it's in static equilibrium, which indicates that the forces that it may feel are balanced. If I was drawing a free body diagram for the spring in the current position that we see, I would draw an upward spring force and I would draw a downward gravitational force that are equal in magnitude but opposite in direction because cancel. So if the weight mg this block was 2 newtons, then the spring force must be upwards of 2 newtons since those add up to 0, right? So this is called the equilibrium position because the block is in its equilibrium position or in equilibrium at this position. It doesn't mean that it only is in equilibrium when it's not moving. I will point out, if I were to pull this down now a little further beyond that position, what would be happening is the spring force vector that I've drawn here would actually be getting a little longer because we already did that earlier in the year. We did a Hooke's Law lab, by the way, where and it was on Pivot Interactives, where the spring force was investigated as a function of, as it depended upon, the elongation of the spring. And you may recall that that was a linear relationship. Hooke's law is in fact indicating that the profile, the force profile on a spring when you pull it, is that it is linearly with the distance that it's stretched. That is to say, if it's stretched twice as far from some other data point you had, then it would generate twice as much force compared to that original distance that you stretched it, an original force in the spring that it generated. No stretching or compression, of course, there's no force in the spring, so that puts 0, 0 as our first data point. And then recall that this might represent, I don't know, 2 centimeters of stretching it, and maybe this represents, I don't know, 5 newtons of force that it generated. If that were the case, then you moved on to the next 4 centimeters. So you're stretching it twice as far, 4 centimeters instead of 2 centimeters. And then you guys discovered that the new force that it generated was 10 newtons. So doubling the elongation doubled the force generated in the spring, the restoring force, again, because when released, boom, it will snap back to its original length. It's restoring itself back to its original profile, right? Original length. And surely when we plotted that out with many data points, it was linear throughout, right? And this was evidence that the spring force was in magnitude proportional to delta x, in direct proportion, meaning doubling the elongation doubles the spring force. And then that allowed us to model that with a linear function, with the y-intercept being 0, 0, indicating no stretch, no internal force. That gives us the y-intercept of 0. X really was now being represented as delta x, how far you've stretched it. On our y-axis was the amount of force generated in the spring. And then you may recall that the slope graph was the spring constant, and that was Hooke's law. The slope was the spring constant. So if this line, this graph that we've drawn on the left side was more steep in its profile, that would indicate, maybe the first data point was actually here when we stretched it to 2 centimeters. That means only 2 centimeters of stretch was actually generating 10 newtons of force, where the original graph I drew, 2 centimeters of stretch was only generating 5 newtons, right? So the stronger K, this second graph that I've drawn would have a larger K value, and this one would have less K. Again, K is the spring constant. It tells you how much force is generated in the spring based upon how much you've stretched it, and the units are newtons per meter. So if the spring constant was, I don't know, let's say 50 newtons per meter, it means for each full meter of stretching the spring, 50 newtons of force would be generated. And again, it doesn't matter if it's a full meter, because most springs can't be stretched that far. You can divide it because it's proportional, right? They're proportional. So if it was, again, 50 centimeters for each 50 centimeters, per whatever I said. In fact, I'm doing that backwards. If it was, I meant to say 50 newtons of force per 100 centimeters, which we would say is 1 meter, then I could divide both of these by 10, for example, and get, well, it should be 5 newtons of force per 10 centimeters, and that might be a practical distance for stretching the spring, right? And you would know that, okay, it should generate 5 newtons of force, right? So that's just a reminder, because I was starting to talk about how the spring force vector in this diagram, the free body diagram, would technically change, right? Based upon what we knew already. Again, longer stretch should cause more restoring force. So if I were to return to what I was showing, which was an original equilibrium position where these were balanced forces, if I am to now pull it down further to this area and stretch it more, then that spring force would increase because it's more stretched more, right? The gravity force, its weight wouldn't. Of course, that doesn't change as you move something around. That would be the weight of the block, right? And really, let me point out, we're really referencing like this spot right here, this end of the spring. That's the point we're actually modeling the forces on, this little end point. The end part of the spring feels an upward pull from the spring above it, and it feels a downward force from Earth's gravitational force acting on the block, right? Point being, if we stretched it here, we wouldn't expect it to stay there, because look at my free body diagram. It's indicating these forces are unbalanced, right? And so when I release it, it would move in the upward direction, because that's the direction of the net force. And that's, of course, what we see, right? I can talk about damping a little bit, but return. Damping is an effect that kind of diminishes its motion due to heat or air resistance. So I've removed that effect. So if I pulled it down like this is going to go up and down, right? However, my point being, if we then paused this and saw that this was now going way up here, right? Now, remember that when I took away this thing, this was its original length right here. So that means if I were to actually compress it above that point, now it's a compressed spring. Which way would the spring force be pushing on the block? Now that would be a downward force, right? And a free body diagram for that scenario would now show a spring force that's down, a gravitational force that's down. I don't know how they are comparatively. Just know there's two downward forces. So for sure, the net force would be down, which is why after this position, it should move down. After this moment in time, it should move in the downward direction because the net force would be down, right? And it would continue moving back and forth between those two extremes. In the middle, it still always passes through the equilibrium position. So this was, at the bottom. This is at the top. The equilibrium position is still in the middle when they are balanced. Those forces are balanced. And my point is that the equilibrium position still occurs every time it passes through that. It might only pass through that for a fraction of a second, but nonetheless, every time it passes through that equilibrium position, which is right about here. So as it goes down and up and down and up, even if it's a momentary, just a small moment in time, it's still passing through the equilibrium position. So we know at that position, the forces are balanced. The upward force from the spring and the downward force due to the weight of the block are balanced, right? So this thing would now go up and down, and we call that oscillating, something that technically goes through a process of moving from one position to another position, but then back to the original position, but back to the other position, and back to the original position. Over and over, it goes repeating itself. Call that an oscillation, oscillatory motion. So that's what we're seeing right now. We're seeing oscillatory motion. Generally, what we want to do in physics is define some of the properties of this type of motion in this type of system. Again, this is usually referred to as a mass spring system because it's composed of two objects, a mass and a spring. They're not very creative with that title. So what are some of its properties? Properties are, again, just measurables. Things that you can measure are a property. My height is measurable, so it's one of my properties, for example. What we notice in terms of the properties, the original ones I'm going to point out to you, are the idea that we can change the weight of one of its components, which is the weight of the object, right? You can change this weight to be small or big. And we notice that when I change it, it changes the aspects of some aspect of its motion, right? When it's a very large weight, we see that it's going through its oscillation in a longer amount of time. The period, in this case, is longer. Period, again, would be the amount of time to go from, let's say, the top back to the top. So I can time it with my watch here. It would be boom, boom, about a second in that case. So I would say that the period, again, is the time to go from any position back to that original position. I could certainly have done it for the bottom. It doesn't matter which I choose. Bottom to bottom, 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 about 1 second, right? So this is the period, right? This period is something that references how long it takes to go through a cycle. And we notice that when we change one of the properties, which is the mass of the mass, that kind of slows its motion down and increases the period. On the other hand, if I were to make it a much lighter mass, less inertia, remembering that this has more inertia, which is certainly part of why it moves so slowly. Things that have more inertia have more resistance to motion and technically to changes in motion. And this thing's motion is definitely changing. Its direction keeps going up, down, up, down. No different than, think of, a medicine ball. If you held out your arms, outstretched your arms out horizontally and held a heavy, 10-pound medicine ball in your hand, and I said, all right, move it back and forth as fast as you can, It wouldn't be too fast, right? It'd be, ooh, slowly it would move back and forth because you would feel the inertia of that medicine ball as you tried to accelerate it, because the speed is changing. It has, by the way, no speed at the top, stops, so it's no speed here. Its fastest speed is in the middle at equilibrium, interestingly. And then at the bottom here, again, it has no speed. There's no speeds at the endpoints. But my point is, it would that motion back and forth would be pretty slow. And again, the acceleration, since it's going from no speed and then has some speed in the middle, it must be accelerating, not only due to its change in speed, but its direction, would be relatively slow going because of its high inertia for your medicine ball scenario, right? On the other hand, if I put a remote control in your hand, say, okay, shake it back and forth, left and right, you can do that much more quickly because it has less, the remote control has less mass, and therefore it responds more quickly to any force that's acting upon it, right? So this changing this property, the mass of the mass spring system, which, by the way, we always ignore the mass of the spring, which in the real world may be something you couldn't ignore. We're assuming that the mass of the mass, we usually refer to this as the mass of the mass is much more than the mass of the spring. It's a negligible amount. So if the spring is only a couple grams and this is 50 grams, then we consider the mass of the spring negligible. So know that in all your problems, the spring's mass is considered small, like the string, like we talk about strings having negligible mass. So we see again that changing the mass of the mass certainly affects its motion. The other property, the other measurable, is the spring constant we talked about just moments ago. The spring constant, again, tells us how strong the spring is. And you'll notice that when I go to a lower spring constant, it's thinner. This is like a weak spring, maybe 2 newtons per meter, which means stretch this thing out a whole meter, and it only requires 2 newtons of force from you to stretch it out to that distance. At that distance, it would pull back on your hand with 2 newtons of force. On the other hand, if it's a much stronger spring, this might be like 200 newtons per meter. It takes a lot more force, 200 newtons, to stretch that thing out a meter, right? And so we'll notice that not only did changing the mass of the mass affect its motion, its properties, so too does the any changing of the spring constant. And we can see that now. If I set this into motion, it goes through its cycle very quickly, right? That's like it has a lot of force, right? Spring generally, as stretched or compressed, generates tons of force. So that would be in my scenario of like the medicine ball, which this isn't a medicine ball. This is pretty light, but nonetheless, let's just imagine you did have a medicine ball in your hand and it was slow in your arms to move it back and forth, side to side. And then we bring in, the Hulk, and we say, all right, Hulk, you do it. He stretches his arms out. You give him a 10-pound, same 10-pound medicine ball, and sure enough, boom, 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 he can move it back and forth really fast because he's strong. Right? He can compensate or he can compensate or counteract. I guess that's the word I was looking for. The extra inertia by just having so much strength in his arms, right? And so he can move it back and forth really fast. That's like the spring constant being large is like Hulk. Okay, so we notice again, it has no problem changing the motion very rapidly when it's large spring constant. On the other hand, if we reduce the spring constant, it's a weaker spring, so it moves back and forth more slowly. That's like me, the same medicine ball in my hands, and this is the medicine ball in the Hulk's hands. You can move it back and forth real quick. Right, so this is a property. The spring constant is one of the properties, including the mass, that changes motion. And we see that there's a correlation with period, right? This, on the other hand, is a very short period. It'd be hard for me to time, but I could try. Boom, boom, 0.2 seconds, 0.25 seconds, about a quarter of a second. Boom, boom. See, that's such a small time. It's hard for me to do it accurately. 0.37, 0.32. It's a small amount of time, right? It's a small period. On the other hand, if I reduce the spring constant, boom, boom, it's a much longer period, right? So we see that there's 2 properties that have an effect on how quickly it goes through its cycle, and it has a direct correlation with the period. Okay, so what we're going to now talk about is how period is correlated with omega. Now, remember that omega was a quantity that we previously referred to as rotational speed or rotational velocity, which now we use the same omega, but we call it angular frequency. It's the same symbol, and it gets the same units, radians per second, in both cases. Now, you might wonder what does this have to do with angles? Why are they mentioning the word angular? I actually have a mass spring system here set up to explain to you that idea. If I were to, so I have a whole set here. I have a whole spring set. Not surprisingly, right? I mean, yeah, I'm at home, but I'm a physics teacher, so I took this stuff home with me in anticipation of today's lesson that I had to provide. So I have a whole spring set, and the primary difference, other than, you know, some are short while some are longer, is that their spring constants are different. Some of them have weaker springs, some of them are stronger springs. K is different for all of them. I've set that very simply here, just on my desktop, just a little pencil that's overhanging my desk, edge of my desk. I have a spring that's been elongated, not because I'm pulling it down, but because I actually hung this weight from it. And there's a little thing taped to the bottom because I'm using my motion sensor to actually record some data, some information about how this thing moves in terms of how its position changes as it oscillates back and forth. And since this thing sends out waves, kind of like an echolocation idea, like bats and dolphins use, and radar, waves bounce off of flat surfaces very nicely, like basketballs bounce off of flat walls very nicely. They just hit and return to the opposite, you know, straight back the other way. So I usually tape these to the bottom because they're nice reflectors for these waves that are going to be emitted from this. So then I just lay this on the ground. It's a very common experiment. A little dark down, but there it is. And now if I were to go over to here, and just hit collect. Now these are graphs that you have to be aware of. They're vital. That critical bits of understanding that you have to have. That this thing goes up and down, its position changes, right? I mean, we'd have to pick an XY axis, of course. If I were to go back to here, this thing's position changes. So usually what we do is I don't like that they only give this particular ruler. It goes from 0 to 100, like a meter stick. Because typically what we do is, let's get back to, well, I guess I can just do that. So typically what we do is, in this equilibrium position, we call this the 0 meter mark. And then so I would like this to be a ruler that goes 0, plus 10 centimeters, plus 20 centimeters, plus 30 centimeters. And then below 0 would be negative 10 centimeters, negative 20 centimeters, negative 30 centimeters, and so forth. They don't have that. They should. Because that's how we track usually the motion of an object that's moving back and forth in the simple harmonic motion manner. So once you've set up your axes and chosen a 0, which this would be, and then let this thing go, its position certainly changes, right? And let me point out another important idea. If I were to pull this down by, I don't know, let's say 10 centimeters, because we just saw that it naturally, left alone, it was in equilibrium right at the 40 centimeter mark. So if I displace this by 10 centimeters, then how high up will it go above this 40 centimeter mark, the equilibrium position? Let's see. In fact, let's go a little further. I'm going to pull it down by from 40, where it normally was, down to 60. So that's a 20 centimeter displacement. Oops, sorry. Try again. Here we go. Now you'll notice that not only is it returning to where I pulled it to, as long as there's no energy loss. Again, damping is this idea that air resistance really removes energy, motion energy from the system, and potential energy, but just, I should say, mechanical energy is lost as it passes through the air, just like the pendulum does. Eventually a pendulum stops, right, because of that loss of energy. And that effect is called damping. Damping means to reduce something over time, reduce something's motion over. So that's why when I put lots of damping like this, it just stops right away. So my point is, if I were to, again, this is the equilibrium, displace it downward by 20 centimeters, 60 mark, and now release it, we see that it goes 20 centimeters above the equilibrium, from 40 to 20, and then back to 20 centimeters below, which is here, because the equilibrium was right in the middle. So it goes, again, this should say 0, which means this would say minus 20. And then the other data point would actually be plus 20. I just missed it, but it was when I was up here, right? So its position would really go from plus 20 to minus 20, plus 20 to minus 20, plus 20 to minus 20, right? It doesn't have to. It doesn't mean that we can model something that has that system of zeros and, a 0 and plus positions and minus positions under it. I mean, it could technically be an absolute scale like this that has all positive. Anyways, let's just see. So when we return back to here, I'm pointing out that's why we have a position versus time graph, because this position changes. 0.2 would represent 0.2 meters. So that's worth me pointing out. So for the real device, the motion sensor I have sitting on the floor, 0 meters just means like it's literally it's laying right on top of the sensor. It's 0 meters from the sensor. 0.2 means it's 20 centimeters, 0.2 meters above the sensor. Remember, my sensor just stays on the floor for this experiment. And then 0.4 would be 40 centimeters above the sensor, 60 centimeters above the sensor, 80 centimeters above the sensor. So although in textbooks and on the AP exam, usually you see this idea that as it moves back and forth, it goes positive position to a negative position, a positive to a negative. Know that we won't see that in this real world scenario, because my sensor only measures positive distances. You're either 0 centimeters away from it, which means you're right on top of it, or you're some positive distance away. That doesn't hurt us, though. We can still understand how this all works. So let's, I'm going to get to the velocity graphs too. We'll do one thing at a time. So here's our position versus time graph, because as time ticks away, the position changes. So I'm now going to pull it down a little bit and release it. So it's oscillating right now, as I think you can see. If you can still see my camera, I believe you can. And now I'm going to hit play, collect. Beautiful data. Okay, so what we can see again is that the position varied from about 0.4 centimeters away from the sensor. That's when it's at its lowest position as it went up and down closest to my carpet. Remember, my sensor is sitting on the floor facing upwards. And then the furthest distance was about, I don't know, 0.55 or so, 55 centimeters. That's up at its highest point when it was 55 centimeters above my sensor. And then on its lowest position, again, it would have been, I don't know, maybe 45 centimeters. Now what we're going to do is point out that the middle of this line, if I drew a line right down the middle here, where would that be? Well, it would be I'm just eyeballing it. Not at notice 0.4 and 0.6, so the middle line is 0.5. Not quite 0.5, it would be a little under 0.5. Let's agree on, if I drew a horizontal line straight down the middle of this, it would be a little under the 0.5 mark, right? Well, I'm going to steady this with my hand right now, the mass, so it's not moving. Now I'm going to hit collect data. Wonder, where will this position line show us? This is referred to as the equilibrium position. Let's see. Remember that the middle line here would be a little under 0.5. There it is, right? That is our equilibrium line. It's not moving right now. It's a little under 0.5, which means when I pulled that thing with my hand down by, let's say, 10 centimeters and released it, that would have been, let's say, down here. It then went 10 centimeters above and 10 centimeters below and 10 centimeters above and 10 centimeters below. And the only reason I'm doing these diagonals with my, it's not really diagonal, it's curve, right, is because although it's going up and down, we're plotting those positions over time, sideways. So as soon as you make a dot, the next dot has to be somewhat to the right because time is ticking away, right? So we know that it will, if I pulled it down by 10 centimeters and released it, then the first data point would actually be right here, if that were the case. And then there would be a point where it was 10 centimeters above the equilibrium, 10 centimeters below, above. And we notice as we collect the data, it's not diagonal lines. It's not diagonal up, diagonal down, like jagged V's. It's this nice sinusoidal shape, which is like a sine function or a cosine function. So it's an important thing for you to understand that the distance you pull it down, which is called the amplitude is the maximum distance from equilibrium. And I already discussed with you where equilibrium was back in the beginning, where we drew the free body diagram. You're seeing it in my camera right now. It's in equilibrium. Forces are balanced. Fg and Fs are equal in magnitude, right? And that when I then pull it, let's say 10 centimeters underneath that position, that means the amplitude of this oscillation should be 10 centimeters. That means it will go 10 centimeters below and then 10 centimeters above, 10 centimeters below and 10 centimeters above. If this was considered zero, like it would be in a textbook, this equilibrium line would actually be 0 centimeters, which means the highest value, the largest value would be plus 0.1 meters, and then the lowest value would be minus 0.1 meters. 0.1 meaning 10 centimeters, right? Plus 10 centimeters, minus 10 centimeters, plus 10 centimeters, minus 10 centimeters. Again, I can't do that because the software doesn't allow for that sort of thing. So we get oscillatory motion, up and down, above and below, above and below. Always equal in amount above the equilibrium as below. Now let's return to what I was referring to, because since we see that there's actually, get it into motion again, so we have to turn to it again, because the question still stands, what does this have to do with angles? Because it doesn't, right? But then I'm like, but it does, but it doesn't, but it does. Physically, when you look at it, there's nothing rotating. There's nothing angular happening here. But when we plot out its position versus time, we do see that this sinusoidal shape and function, like a sine function, it has a certain period, right? The period is where my mouse is, which is right here, all the way up, all the way down, back to the middle. So I'm doing it with my mouse right now. Boom, just to the middle. That's one cycle. Because this is again when it was above at the highest point, the equilibrium. This is when it was below at the lowest point, and this is when it returns back to the equilibrium. For this data, the first data point happened to be just randomly, because I clicked play randomly as it moved up and down. But that first data point happened to be right in the middle when it was right passing through equilibrium. So then it was above, then it went lower, 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 passing through the equilibrium in the downward direction, then at its lowest point, and then starting to go back up again. And then as it passes through equilibrium again, since that's where it started, that would be one period. Now, on this graph, we would reference that as time, right? So from here to here, I could kind of ballpark the period as, well, a little less than 1 second, maybe 0.9 seconds. The period is about 0.9 seconds, right? So then when you'd say, well, and what does that have to do with the angle? Well, that's technically one cycle, right? How many radians would we consider that one cycle that I'm doing again with my mouse? How many radians would that be? Well, that's like 2 pi radians, right? And that tells us that for each time it goes through a cycle, since the graph is actually angular in nature, since it's sinusoidal and it goes through cycles, and one period of time we associate with 360 degrees or 2 pi radians, then omega is a quantity that is relevant here, because it will tell us how rapidly it goes through its cycle. So this right now, what we're seeing again is about 0.9 seconds. If I were to go back to here again, in fact, I have another one that's here. So know that you're going to see vertical mass spring systems. You'll also see horizontal mass spring systems, as we see here, where the spring is attached to a wall. The x equals 0, you notice, is right in the middle, right here. And this would be like, plus 0.2, and this would be like minus 0.2 meters, plus 0.2, minus 2, right? And I can hit play. And we just, assuming that somebody pulled it, of course, somebody has to pull it originally or compress it and then release it. Either way, once you do that, it will continue moving back and forth. The rate, how rapidly it goes through its cycle, again, it's correlated with omega. So if I wanted to change omega, which we previously saw was affected by both these properties, right? If we call this a large omega, since it's going through the cycle quickly, many radians per second, much of the cycle is completing cycles very rapidly, which, by the way, if we were graphing this one might look like this. So this would be like a large omega. I guess you don't usually use the word large. You'd say high omega. On the other hand, if I were to go like this and see what that graph looked like, it would look more like so this is a low omega because it's not going through its cycles very quickly. This, if I drew a dotted line here, I'd say, boy, this top one up here went through its cycle in like, I don't know, 0.2 seconds. While this other one barely even went through a certain, small portion of a cycle in the same 0.2 seconds, right? So omega visually is how compressed these graphs are. If it's a highly compressed graph like this, then that's a small period. This would be a small period, and it'll be a high omega. So small capital T, remember capital T stands for period, high omega. Down here, the lower graph, which is what I'm showing here, this would be a long period, which you can see it's taking much more seconds to go through a cycle, right? Start, stop, that's like a full second. But that would be considered a low omega because it's not going through its cycles very rapidly, right? So there's an inverse, notice that there's an inverse proportion there, just on this idea. There's an inverse effect when period is long, like we're seeing now, omega is low. On the other hand, when omega is high, oops, I didn't mean to do that. On the other hand, when, in this case, omega is high, going through cycles much more quickly than this. So when omega is high, the period is small, right? And we actually already knew that, right? We already have omega equals 2 pi over t from before, right? We still get to use that. Just pointing out that this is now referred to as the angular frequency. We call it the angular frequency. Again, it's still in radians per second, which tells me if omega was 2 pi radians per second, then and this top graph that I have is let's just say modeling this thing's motion up and down. If omega was 2 pi over 1 second, back to the bottom formula, 2 pi over a period of 1 second, 2 pi over 2 pi radians per second. That would mean this would be the 1 second mark right here. Oop, I didn't take that back. That's not right. That means this spot right here would be the 1 second mark, because this that I'm coloring in, that would be 1 full cycle. And if that were the case, then omega would be 2 pi over 1, 2 pi radians per second, right? On the other hand, if the period was like 4 seconds and I put 2 pi over 4, well, 2 and the 4, that'd be pi over 2, right? That means that in that same 1 second of time, it doesn't go through 2 pi radians. It only goes through pi over 2, right? Which would be 1/4 less of its cycle. That would actually correspond to this spot. If I had drawn it perfectly, it would be like right there. Because this represents 1/4 of its cycle, not perfectly drawn. So now we get to point out that since we connected, again, omega, I've talked about the shape of the graph and omega. Now, omega is an important property that's affected directly by the mass of the object that's going back and forth and the strength of the spring constant. Which, again, by the way, if I run this is moving again very slowly. On the other hand, if I were to increase K, reminding you that a stronger spring should go through its cycles more quickly, which it clearly is. A weaker spring, like this one, 5 newtons per meter, goes through its cycle more slowly. Or you can keep K the same, and now just change the mass. Again, I could make this much less, like 0.2. Oops, sorry, 0.2 kilograms. Try again. 0.2 kilograms. Oh, 1 is the minimum. Sorry, 1. Well, let's just leave it at 1 then, and run it. Pretty slow, right? On the other hand, if I were to put much more mass on here, let's say 4, play it, the same spring constant, I'm going to go much more slowly through its cycle, right? So reminding you that there's that connection again. So how do we model this with equations? The first idea, formula, omega is 2 pi over t. Omega is the angular frequency again. How frequently it goes through its cycles is how I think about it in radians per second. And t is the period in seconds, the time to go through a cycle. However, we saw that there was a connection between the spring constant and omega. Remember, there's this connection between omega and period, right? So when K was large, when K was big, omega was small. I didn't mean to say that. It's backwards. When K is strong, which we saw in the image, when boom, 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 back and forth, omega is very strong, or a very, very large number. And on the other hand, when K is weak, or it's a weak spring, so it's a weak spring like this again. This is a low K value and a small omega, a large K value and a high omega, right? We also see that how the mass affects it was that when, let's just say we leave it like this, it's going through, there's some omega that we're seeing now. If I increase the mass, omega goes down. So and then mass goes down, omega goes up. Mass goes up, omega goes down, right? An inverse relationship there. So we know that there's some sort of proportional relationship between omega and K, because they kind of mirror each other. And we see that there's an inverse proportion between, I shouldn't say equals, there's an inverse proportion between the mass and omega. So in order to know what the actual formula is, you'd actually have to do an experiment, right? Which we can do. We're going to do it here. So I'm going to reset this, and I'm not going to go full lab right now. I already know what this result is. I'm just going to try to show you the idea behind it. if I were to leave the mass as 1 kilogram, and which, by the way, how far you stretch it, the amplitude has no effect on how rapidly it goes back and forth. That's similar to the pendulum, which you might remember. If I bring back pendulum from this equilibrium, just hanging straight down, and I draw it back just a little bit and let go of it, it slowly goes back and forth with, let's just say, a 1 second period. On the other hand, if I pull it way back up in the air and release it, and boom, goes back and then boom, back. Wow, it's still a 1 second period. You guys remember that, right? That's amplitude. How far you draw the pendulum back from the equilibrium, that's a middle line, middle dotted line that goes straight down the actual pendulum. How far you draw it back from that before you release it's called the amplitude. And that had no effect on the period, right? So pointing that out, amplitude and period are not correlated. There's no correlation there. With that said, let's just do one. So 0 seconds. So let's play one, run. .25 seconds. So I'm getting a period of 1. That's how long it took to go all the way there. If I were to now quadruple, let's just write that down, 1.25 seconds. So trial 1 with 1 kilogram of mass and 5 seconds. Now we're going to do another trial. That's very specific because I already know what I'm going to do. So we look like I lost connection with my whiteboard. Sorry, give me a second. Not sure why that happened. Because I started writing stuff and it's not coming out on my. There we go. So now we're doing trial 2, where I'm going to quadruple. I'm going to quadruple the mass from 1 kilogram to 4 kilograms to test if there's some either square relationship between period and mass or square root relationship. And we'll find out. I've quadrupled. I'm increasing the mass up to 4 kilograms. So that means the mass is increasing by a factor of 4. Let's see what happens to the period. Go ahead and run. Oh, what happened? So 0 seconds. Oh, I hit the reset button. So sorry. Try again. Run. I hit pause. 2.53. About 2.5. 2.5 seconds. So what we notice is, going back to this, that now I get a period of 2.5 seconds. Now notice that it's half. Well, the first trial was half of the period. This new trial was twice as much time. So we notice again that there is a mathematical correlation here, not just some random correlation. They're mathematically connected. So the period increased by a factor of 2, right? So that tells me if the mass goes up by a factor of 4, square root of 4 is 2. The period goes up by a factor of 2. That tells me there's a square root relationship between mass and period. Now I can say, all right, mass is proportional to the square root. I didn't mean to write that. Right? That the period is proportional to the square root of the mass. Because that's what the data on this, yeah, it's a virtual simulator, but that's a bit hard for me to do. Though I have my setup here, I didn't bring, unfortunately, 2 masses where one of them is 4 times as much. I should have, but I didn't. But trust me, it comes out exactly the same. So that tells us there's a correlation between period and mass, that there's a square root. There's a square root relationship there. And recall that omega is equal to 2 pi over t, right? That tells us, since there is an inverse relationship between omega and t, that there should technically be a result where omega is inversely proportional to the square root of the mass. Right? Because I can technically take away my t and put 1 over omega here, right? I technically could have taken t here and put 1 over omega, since there's that inverse relationship that I just highlighted here. And then if I reciprocate both sides of this, I get omega is proportional to 1 over a square root of mass. Right? So that's one key thing to know. Omega is inversely proportional to the square root of the mass. And now we do another test to see what is the connection with the spring constant. So I'm going to return back to here, and we'll use the same trial 1 that we had before. Trial 1 will be the same. What was trial 1? Mass of 1 kilogram, 1.25 seconds. And now and that was with a K value of 25 newtons per meter. So now we're gonna do the same idea here. We're gonna quadruple the spring constant to make it 4 times stronger. So K is going to go up by a factor of 4. And our question is, what's going to happen to the period? What do you think? If we're making it a stronger spring, should the period be less time or should the period be more time? Remember, stronger is like Hooke. Boom, 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 back and forth, the medicine ball. Let's see. So I'm going to go ahead and type in 100, intentionally increasing K by a factor of 4. Leaving the mass the same, of course, I wouldn't want to change that. I'm trying to see if there's a correlation between K and the period. And let's run it. Oops, sorry, reset. Trying to run. Oops, it's happening so quickly, I can't. Sorry, reset. Run. Okay, now pause it. Now I can go 1 frame at a time. Back 1. I'm getting 0.63 seconds. So when I compare these two, this is half of this, right? This is like 63 cents. Well, twice 63 cents would be $1.26. Pretty close, 1.25, $1.25. Right? So this tells me that the period actually went down by a factor of 2. So it's the opposite of what we previously saw. Still a square root relationship. When K goes up by a factor of 4, square rooting 4 gives us a new factor of 2. The period will therefore go down because we know there's an inverse relationship. We already knew that, right? Weak spring has a certain pace at how rapidly it goes through its cycle. Strengthen up the spring, and it's going to go through. It's going to be a larger omega and less time, right? Less time. We were expecting less time. That makes sense. And sure enough, we got less time, right? By a factor of 2. That means the period decreases by a factor of 2. So that tells us that the period has an inverse proportion to square root of K. That tells us again that K were to go up by a factor of 4. You can imagine putting in the number 4 here and then applying the square root that's around it. 2 comes out of that. Then again, since K going up causes T to go down, since they're inversely proportional based on the way we've written it here, if K goes by a factor of 4, the period would go down by a factor of 4 if there was no square root there, but there is a square root there. So if K goes up by a factor of 4, period goes down by a factor of square root of 4, which is 2, right? So now we have two results here. We end up with this one here. Omega is proportional. Oh, sorry, I have to connect omega into this. So let's do that. Since omega was equal to 2 pi over t, right? And since omega and t are inversely proportional to each other, it's like my board has frozen again. Not sure why it's doing that. Sorry. Oh, it finally went through. Okay. So since omega and t are inversely proportional to each other, right here, right, that means I can take away my t and put 1 over omega, just working out relationships. That tells me that there's a direct, these two on the bottom are directly proportional to each other because they're both in the denominator, but on opposite sides. So that tells me I know omega is there, because I could technically flip both of those. Right? I could flip this one up and flip this one up, and I'd get omega is proportional to the square root of k. Right? So now we have 2 results. This is giving me a headache. Those bar graphs. So we end up with 2 results. The top right shows omega is inversely proportional to the square root of m. And then in another experiment, we know what I have here on the bottom down here. Omega is directly proportional to square root of k. So now we can combine those. We just have to superimpose those. Again, we have omega is proportional to root k. That's what we had. We have omega is inversely proportional to root m. So if those now just overlap, you get this. Very laggy. My screen is very laggy. I'm sorry for that. And then since they're both square roots, we can just go like this. So this is the formula for omega. Omega is equal to the square root of k over m. This is a well-known formula for the angular frequency. Again, this is the angular frequency, which just in your mind tells us how rapidly it will go through its cycles, just conceptually. If k is strong, then omega should be pretty high, boom, 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 back and forth. If k is weak, small number, then omega should be very slowly going back and forth. Omega would be small. Conversely, if m is really large, if it's as heavy as an elephant, like this, it'll take a long time to go way down and way up. Large mass would generally have a low omega. On the other hand, if you make it really light, small mass should be high omega. Small mass, large omega. But there's that square root there that you'd only get through experiment. Okay. So with all of that said, I think I'm going to end my video here. It just says video 1, because in the next video, which I'm probably going to stop in a moment and just start recording up right away, we're going to return to these graphs to think about, well, how do we connect this information, omega? How does that play a role in these, how you model these? We're going to start talking about sine functions, cosine functions, how this piece fits into it. And then we're going to model. I'll show you how it's modeled. And then we're going to look at other properties, which is not just the position that's changing. The speed physically changes as well, right? We could see that the data that I collected is indicating that there's a change in speed, right? Which again, remember that we said that when it's at the top and the bottom, which is here and here, when it goes, this is for something going up and down, let's say, or it could be left and right, which the 2 endpoints on the left and on the right would still be these 2 points. That we said it stopped, right? On the 2 endpoints, it stops because it has the reverse direction, no speed, right? So I'm just throwing this out there. When you compare those 2 graphs, a position versus time graph versus a velocity versus time graph, and you trace down an endpoint straight down with a line that goes straight down, where does it land? Boom, right there. See, no, that's 0. No velocity when it's at the top. How about when it's at the bottom? Boom, 0 when it's at the bottom, which we know, right? Makes sense. There's these at the top and the bottom, known as the max and min of its position, since it stops because it has to reverse direction, that should correlate on a velocity versus time graph to zeros, right? On the other hand, we see that when it's passing through equilibrium, passing through the middle point, moving along quite well, right? We're not talking the endpoints. slow this down. It's too hard to look at. So 0 speed there and 0 speed instantaneously there. But we're referring now to right there, the middle, right as it passes through the equilibrium line that we talked about. What would the speed be? Conceptually, it's a maximum. It's moving at the greatest speed because after this position, the upward, remember, there's a larger upward force vector in this position here. Where is my, did I lose my, oh, here it is. Remember that at the bottom, when it's way stretched down like this, and this is the equilibrium line, let's say here, and it's way down here, there's a huge upward spring force compared to the weight, right? And if it's actually moving in the downward direction and there's an upward force, or a net force, I should say, that's up because the extra amount of force is up, and it's moving down, then that means it should be decelerating and slowing down as it goes into this bottom position, right? On the other hand, once it hits the bottom and then it starts moving in the upwards direction, V is now up, now already at its bottom position, moving in the upward direction. The net force of up, moving up, it's going to accelerate. It's going to gain. It'll end up having a maximum speed as it passes through the middle, right? And then when it's up here, when it's really compressed above the equilibrium line, now you end up with, or let's say it's not fully compressed, but it's kind of moving towards that position, still moving up, but not at the fully compressed state yet. Now you've got, again, two forces, the spring force and the gravity force are down, so the net force has to be down, right? And if it's still kind of drifting upward, hasn't reached its highest point, moving upward with a net force of down, again, it needs to be slowing. When it hits the top, it stops, no speed. And then again, as it starts to move down again, the velocity is now down. The net force would still be down. The net force is down all points above equilibrium, the net force is down. All points below equilibrium, the net force is up. When it passes through equilibrium, what is the net force? 0, right? When it passes through equilibrium. And so my point is, on the way back down, after it's already hit its highest point, it would then therefore again be going down. Net force is down, speeding up. Max speed here in the middle again. And then as soon as it dips below that, it's now moving down again. The net force is up because the spring force is actually stronger below that line than it weighs, and it's slowing, stop, right? So the maximum speed has to occur in the middle. Interestingly, when there's no net force, when it's at its equilibrium position, that is actually where you would expect the maximum speed. And that's what we're seeing here. When you look at this position graph, again, here's the top when it's up in the air. Here's the bottom when it's all the way to its lowest point. So where would the equilibrium be? Right here in the middle. Boom, right there where my cursor is. So if we trace this down perfectly straight, I wish I had a straight edge to do that on here. I don't. Boom, it brings us right here. So that tells us it's moving really fast, but it's a negative value. Why? Because it's moving which way? As it passes through equilibrium, it's moving down, passing through equilibrium in the downward direction. That corresponds to this position. How about this one right here? This is another point where it's passing through equilibrium, right where my cursor is. Let's trace that down. Boop. That gives us a positive velocity. And notice they're the same. They're symmetric. Looks like the lowest value here is negative 0.4, and this is plus 0.4 meters per second. This is velocity, so plus and minus again indicates plus is up, moving up, minus is moving down. So when we check this other equilibrium position, it has a positive 0.4 meters per second. That's because it's moving up. It's on the way up, passing through the equilibrium position, right? It's a very important part that you need to understand, that at the end points, top and bottom, it stops. Those would correspond to 0 speeds, as I'm showing here. And then when it's at the equilibrium positions, moving through the equilibrium positions, Speeds are maximum. Boom. 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 Again, the only difference being plus and minus because it's either moving up through passing through equilibrium or moving down negative passing through equilibrium, right? So in the next video, we're going to talk more about position, velocity, and we not surprisingly have to start talking about acceleration graphs too, because acceleration depends on forces. If the forces are varying up and down as it goes up and down, as I showed, right, the spring force isn't constant. The weight is constant, but the spring force isn't constant. So if the net force is therefore changing as the spring force continually changes, then based on Newton's second law, F net equals ma. Well, if F net is varying up and down more and less, then the acceleration must also be varying less, more and less, because F net is proportional to A. So there's three graphs: position versus time graph, velocity versus time graph, and then we'll talk about the acceleration versus time graph, and then we have to model those. That will be the next lesson on how we model those. All right, that'll be it for this lesson. Hope that was helpful. See you soon.